Now that you've had a chance to think about how the root inspection problem works, we're going to look at solving that problem. So first we'll review the statement of the root inspection problem so that we're all on the same page. We'll review how to interpret walks as multigraphs, as that's going to be really important to us for actually solving the problem. We're going to reinterpret Eulerian circuits as solutions to some of the root inspection problems, which is not the way we were thinking about it when we started with Eulerian circuits. Then we'll use what we know about odd degree vertices in graphs and Eulerian circuits of multigraphs to figure out how to determine an algorithm for solving root inspection problems in general. All right, so just a reminder about how the root inspection problem works. If G is a weighted graph, in other words, it's a graph where each of the edges has a weight associated with it, how do we find a walk that satisfies each of the following conditions? First of all, that walk has to cover every edge in G. It has to end at the same vertex where it begins. And another way of saying that is it's a closed walk. And the total weight of the walk is as small as possible. And what we mean by the total weight of the walk is the sum of all the weights of all the edges crossed in the walk, where when we cross an edge more than once, we count its weight the number of times it is crossed. So note that every solution to a root inspection problem is a walk, and every walk can be represented by a multigraph. And just to remind you what a multigraph is, it's a pair VE, where V is a set, that's the set of vertices. E is a set of edges between elements of V, and in a multigraph, we allow that maybe more than one edge can be between a pair of vertices. Doesn't have to be more than one, but it can be. And note that we use multigraphs to help us construct solutions to our root inspection problems. And in general, we use them to model walks. So it turns out, just purely by accident, we have already solved some root inspection problems. If we take an Eulerian circuit of a graph, if it exists, that is going to be a solution to the root inspection problem. The proof of that is pretty straightforward. An Eulerian circuit crosses every edge precisely once. That means it crosses every edge, so that, and it's a closed walk. And the only way a walk can have a smaller weight is if it somehow misses an edge in that Eulerian circuit. But since the Eulerian circuit has to cover all the edges, that means it misses an edge in the graph, which can't happen. That means Eulerian circuits have minimum weight, and that means they're solutions to the root inspection problem. So, since Eulerian graphs are precisely graphs in which every vertex has even degree, this gives us solutions to our root inspection problem for all of those graphs. So let G be a graph in which all vertices have even degree, then every Eulerian circuit is a solution to the root inspection problem. So what happens if we have some vertices of odd degree? Here's an example. Well, first thing we have to do is let's identify the vertices of odd degree, and right there, B and E, those are our odd degree vertices. Those each have a degree of 3. Find the shortest path between them. It turns off BDE is the shortest path between B and E. And there it is with the blue edges. We're going to double edge in this shortest path. And what happens when we do that is now in this new multigraph, every vertex has even degree, which means we can find an Eulerian circuit. And that Eulerian circuit is going to be a solution to our root inspection problem. So let's see, the root inspection solution is going to be, well, we're going to start at A. Let's see, we're at A, we go to B, then we go to C, then we go to D, back to B, back to D again, down to E, back up to D, then to F, E, C, and A, and you can see all of our edges turn blue, which means they all got covered. They all got covered exactly once in the multigraph, twice the edge between B and D and E, and that gives us our solution. Now our total weight is 50, and an easy way of getting the total weight in general is take the total weight of the graph, just all the edges, add up all their weights, and then add in the repeated edges. We get 5 and 2, that gives us 7, so we have 43 plus 7 gives us 50. Now that was pretty straightforward, but we were also got a little bit lucky because we had 2 just two edges or two vertices with odd degree? What if we have more than two odd degree vertices? Well, here's how we can handle that situation. Look at the odd degree vertices and put them all in pairs. Find the shortest path between each pair of odd degree vertices. Add the weights of the edges of these shortest paths, and do that to all possible ways that we can put the odd vertices in pairs. The one that has the lowest total weight is the one we're looking for. These paths will be the repeated edges in our root inspection problem solution. And then we'll get a walk from the Eulerian circuit in that multigraph that's made from those repeated edges, and then we just have to convert those into a walk. So now that you have an idea of the algorithm that we're going to use for these root inspection problems, go ahead and apply those to the graph in the PDF file included with this video. It's called More Root Inspection.